All right, future chemists, doctors, and rocket scientists. Let's get down to some business here. We got some stuff to talk about. All right, so I'm in the note packet here. Looks like I'm on page 10. Okay, and we've been focusing a lot so far on the nucleus of the atom, right? The protons and the neutrons, right? We know that protons identify what the element is, right? And what properties it's going to have. And the neutrons can change the mass, right? Give us different isotopes. Okay, so today I want to focus on the other part of the atom, right? The electron cloud that surrounds the nucleus. Okay, so on page 10, you might see some stuff here that looks pretty familiar, right? You should have talked a little bit about waves in physics class last year. Okay, so I've got a picture of the electromagnetic spectrum here. Okay, and remember, all waves are part of the electromagnetic spectrum. We are mostly concerned with this portion right here, this little rainbow. That's the visible portion. Okay, because that's the part of the waves that we can see with our own eyes. Okay, but it does include other things like radio, microwaves, infrared, right? We use a lot of that for remotes, right? For your TV and whatnot. Ultraviolet, like with the sun, right? X-rays, gamma rays, right? And a whole bunch of other ones as well. Okay, so remember, it's a spectrum, so it's continuous, right? And as I go from one side to the other, right, my wavelength, right, is going to be increasing, and my frequency is going to be decreasing. So, for example, here, if I'm looking at my visible spectrum, right, I'll just focus on that for right now. Over here in the red, okay, my wavelength, and if you remember, wavelength is symbolized by the Greek letter lambda. Looks kind of like an upside down Y. Okay, my wavelength is high. Right, it's a very large wavelength, and my frequency, which I'll just use F, because it's a high wavelength, it's a low frequency. Likewise, as I go across, okay, over to the blue or violet side, my wavelength here becomes, I wrote it backwards. There we go. My wavelength is going to be low, and my frequency is going to be high. Right? They're going to be opposites to one another. Right? And we can see that here. Right? Here are some examples of waves of different colors. Okay, I got violet, right, with a short wavelength, right? It's only 400 nanometers. Okay, that's the shortest of all the colors. And then, or visible colors, I should say. Red down here at the bottom, 609 or 65 nanometers. Okay, so red has the longest wavelength. Right, that's from one point of the wave to the exact same point on the next wave. Okay, so in this point, crest to crest. Okay, so 665 nanometers for red, all the way down to 400 nanometers for violet. We got everything in between. Okay, so then our frequency would be, like, if this was all 1 second here, right, I would count up, for my red ones, okay, my wave is repeating, okay, from there to there is 1, then 2, 3, 4, 5, 6, looks like 6.5 times. So I'll just say 6.5. Okay, and then my violet up here at the top, okay, from here to here is 1, then 2, then 3, then 4, then 5, then 6, then 7, then 8, then 9, 10, 11. Looks like 11 times. Okay, so violet, because it has a shorter wavelength, is going to have a higher frequency. Okay, red with a longer wavelength is going to have a lower frequency. Okay, so why don't you guys take a moment, pause the video, and try answering these questions. This should be review for you from physics. All right. Let's go ahead and let's take a look, see what you wrote down, see if you agree with what I got. Okay, the speed of light for all electromagnetic radiation, that is 3 times 10 to the 8th meters per second. All right, regardless of the color, red, orange, yellow, infrared, ultraviolet, X-rays, or whatever, it's always 3 times 10 to the 8th. Okay, number 2, the distance between two crests of a wave. That is my wavelength, right? So I'm just going to abbreviate there. The amount of waves that pass a given point per second, right? How often the wave goes by is the frequency. Which light has the longest wavelength? If I'm talking just about visible light, longest is red. Which one has the lowest frequency? Which one repeats the least? All right, we saw that, and when we counted those up, that was also the red one. Okay, which light has the shortest wavelength? That was violet. Right, and because it has the shortest wavelength, violet also is going to have the highest frequency. Okay, so make a statement about the wavelength of light, how it compares to the frequency of light. Well, if I have a long wavelength, I have a low frequency. If I have a short wavelength, I have a high frequency. Okay, so we could say that as wavelength increases, frequency decreases. They have an inverse relationship. Okay, likewise, as my wavelength decreases, my frequency increases. Okay, so they're always going to be opposites of one another. So, what do we need to be able to do? Okay, flip it on over. Okay, one of the main things we need to be able to do is use our frequency and our wavelength. Okay, and we want to be able to calculate one given the other. Okay, and the way we're going to do that is using this equation right here. Okay, C equals lambda times frequency, wavelength times frequency. Okay, C is that 3 times 10 to the 8th meters per second, right? This is the speed of light. Okay, so that's always going to be 3 times 10 to the 8th meters per second. It's a constant. Okay, my lambda is my wavelength. Make sure that we are in meters. And my frequency is going to be in reciprocal seconds, 1 over seconds, seconds to the -1, or we could call it hertz, Hz. Okay, those are all the same unit. Okay, so let's see here. What is the frequency of red light with a wavelength of 665 nanometers? Okay, so we've already been given the conversion from nanometers into meters, right? Because we're talking about very, very small waves. A nanometer is 1 billionth of a meter, right? So take a meter stick, divide it up into a billion equal pieces. That's a nanometer. Okay, so very tiny. Okay, so I've got my wavelength. Okay, 6.65 times 10 to the -7 meters. All right, I know my speed of light, 3 times 10 to the 8th meters per second. All right, so then I can solve for that frequency by using my equation. Okay, so I'm going to take my speed of light, 3 times 10 to the 8th, okay, equal to my wavelength, 6.65 times 10 to the -7, and I'm going to multiply that by my frequency. So I just got to divide both sides by my wavelength. Okay, so those cancel out. Okay, so I'm going to go to my calculator here, 3 times 10 to the 8th. I'm going to divide that by 6.65 times 10 to the -7. Okay, and my frequency ends up being 4.5. I'll do 4.51, 2 decimal places, times 10. Now don't forget the times 10 part. On your calculator, that's often going to have the E, and then mine says E14. Okay, so that means times 10 to the 14th power. Okay, don't forget your units. I'm going to put in reciprocal seconds, 1 over seconds. Okay, so there's my frequency. All right, why don't you guys pause, try out number 2, see if you can solve this one. Okay, number 2, I have an AM radio, and it's being calibrated in frequency. A certain AM Brockville radio station broadcasts at a frequency of 803 kilohertz, or 803,000 hertz. What is the wavelength of the radio waves expressed in meters? Okay, so I know I'm still going to use my equation. The speed of light equals my wavelength times my frequency. Okay, so I've got my speed of light is a constant, 3 times 10 to the 8th equals wavelength times frequency. We were given our frequency in hertz, 830,000. Right, in hertz, I'm going to change that to reciprocal seconds. So the same thing, I'm just swapping it out. Okay, and don't forget this one is in meters per second. Okay, so I'm putting the seconds there because that's going to help me cancel the seconds on my left side here. Okay, so all I got to do is divide both sides by my frequency. So 3 times 10 to the 8th over 830,000. Okay, and that's meters per second, and this one's 1 over seconds. Okay, that's equal to my wavelength, which is 3 times 10 to the 8th over 830,000. I end up with 361.4 meters. Okay, now this is much larger than the ones that we're looking at with the visible light, but you got to remember this is a radio station. Okay, radio waves are much bigger, right? Radio waves are all the way over here, and here's where our visible spectrum is. Okay, so this is a much larger wave. Okay, so we also want to take a look at a wave and be able to tell about its energy. Okay, so we have another equation, okay, that relates frequency and energy, and that's this equation down here, okay, where E is my energy calculated in joules, F is my frequency again, and then H is a constant. This is what we call Planck's constant. Right? And Planck's constant is 6.626 times 10 to the negative 34 joules times seconds. Okay, so it's a pretty simple equation. You just got to make sure you're punching in the numbers correctly because there's a lot of scientific notation here. Okay, so let's try out number 5. All right, make sure you're trying this out too. Make sure you can get the same answer that I do. Okay, so let's calculate the energy of red light and the energy of violet light. Okay, so for red, let's do that one over here. Okay, red, we are given the wavelength in meters. So my plan of attack here is I know I have an equation, speed of light equals the wavelength times frequency. Right, but that doesn't have energy. Okay, but I do know I also have energy is equal to Planck's constant times frequency. So if I can get my frequency in the first equation, right, I can bring that over to my second equation and solve for my energy. Okay, so let's do that. Right, I am starting off with 3 times 10 to the 8th equals 6.65 times 10 to the negative 7 times my frequency. All right, we already calculated this out. All right, my frequency up here for my red light, that was this guy right here, 4.51 times 10 to the 14. All right, and that was in reciprocal seconds. Okay, so now I'm going to take that frequency and I'm going to plug it into my other equation. Okay, so I'm going to do energy is equal to Planck's constant, 6.626 times 10 to the negative 34 joules times seconds, times my frequency, 4.51 times 10 to the 14 reciprocal seconds. Okay, so seconds and reciprocal seconds are going to cancel out because one's on top, one's on bottom. Okay, and when I punch this in, 6.626 times 10 to the negative 34 times 4.51 times 10 to the positive 14. All right, that energy is going to be 2.99 times 10 to the negative 19 joules. Okay, so be very careful. Again, there's a lot of scientific notation going on here. Make sure you're plugging into the calculator correctly. Make sure you can get the same answer that I've got here. Okay, next up, why don't you guys pause and try out doing for the violet. Okay, violet, we're going to do the exact same thing like we did before. I'm going to do 3 times 10 to the 8th meters per second equals my wavelength. This time we're using 4.00 times 10 to the negative 7 times my frequency. All right, when I solve for the frequency of violet light, I'm going to take 3 times 10 to the 8th divided by 4 times 10 to the negative 7, and I get 7.5 times 10 to the 14 reciprocal seconds. Now I can take that, plug it into my other equation for energy. All right, so Planck's constant, 6.626 times 10 to the negative 34 joules times seconds times 7.5 times 10 to the 14 reciprocal seconds. Whew, it's a mouthful, right? I'm going to plug that in, 6.626 times 10 to the negative 34 times 7.5 times 10 to the positive 14, and I end up with 4.97 times 10 to the negative 19 joules. Okay, very important here that you don't forget that times 10 portion on either one of those. Okay, because we're talking about very, very small amounts of energy. Okay, so we want to make sure that we know how to do that. Okay, so there's going to be some practice problems with calculating our light and our energies, okay, our wavelengths, frequencies, all that jazz. Okay, so why is all this stuff